Hi, and welcome back to Understanding Motors. In the last several episodes, we've been working towards developing a method of producing a smooth and optimized torque in a motor. Last episode, we finally arrived at this optimal modulation method, the alternate reverse space vector modulation pattern. However, while we now know some information about it, we haven't yet talked about how to actually perform space vector modulation practically. By the end of this episode, we will have described how to use this information in the real world. So, let's get into it. I want to start off this week by offering a quick clarification about what we talked about last episode. After releasing it, I went back and watched the video and realized I may not have been super clear about a couple of things. First of all, the voltage pattern I introduced last week when we were talking about space vector modulation is a type of space vector modulation. Referred to as the alternate reverse sequence pattern, it's arguably the most common space vector modulation pattern. More broadly though, space vector modulation is just the modulation in space of your voltage vector and thus your magnetic field vector to any arbitrary angle, generally while maximizing your utilization of your entire voltage range. Other space vector modulation patterns do exist, and depending on what you care about most, they may be worth looking into. I'm going to link both a paper and another video that talks about how to perform different methods and what their benefits and shortcomings are in the description below. So now, let's look at how to actually perform this so-called alternate reverse sequence PWM, and really space vector modulation patterns more generally. We're going to start by first going back and looking at how we performed our voltage modulation during our 6-block commutation. Recall that a PWM period can be divided into two phases. The forced phase, where current is being actively driven by an applied voltage, and the unforced phase, where it is not. The percentage of the PWM period spent in the forced phase is known as the duty cycle. During the forced phase, when performing block commutation, as we rotated our motor through a revolution, we always had exactly one leg of the H-bridge being PWM to high voltage, and exactly one other being PWM to ground. So, during the forced phases of the PWM cycle, we were using one of these 6 possible H-bridge configurations, depending on rotor angle. To both simplify my depiction of the H-bridge and to make it, in my opinion, more visually pleasing, going forward I'm going to depict the H-bridges like this, where each circle depicts a MOSFET and being colored in yellow indicates being connected. Additionally, I will show the vector of voltage produced by each. As we talked about in episode 7, the configuration we use during the unforced phase varies with our switching scheme, where, if we're hard switching for example, each of these 6 active configurations corresponds to the same completely disconnected H-bridge. If we're using soft switching, these 6 active configurations each correspond to one of 3 unforced configurations. And if we're using complementary switching, these 6 active configurations correspond to one of 3 different unforced configurations. Just like our earlier commutation scheme, with space vector modulation, our PWM periods will be divided into a forced and an unforced phase. Unlike with block commutation, however, where one of our motor phases is always left floating, that is to say, neither connected to high nor to ground, during space vector modulation, we constantly want all 3 of our phases connected to either high voltage or to ground. So, instead of the configurations we use during the forced phases of block commutation, we will use the 6 configurations which involve having all 3 phases being connected in order to drive current. I'm going to describe these voltage configurations as voltage configuration 1, 2, 3, 4, 5, and 6. Obviously, just like with block commutation's voltage configurations, each of these 6 configurations points to a unique and discrete angle. So, in order to produce a voltage vector which turns continuously with the rotor, we're going to further subdivide our forced phase of our PWM period into what we will call T1 and T2. During T1, we will apply the voltage configuration which produces the field vector which is closest to our desired vector in the clockwise direction. Then, during T2, we will apply the voltage configuration which produces a vector closest to our desired vector in the counterclockwise direction. The duration of T1 relative to T2 will be determined by the desired vector's orientation relative to the vectors generated by the 2 chosen voltage configurations. Unlike our previous commutation schemes, during the unforced phase of the PWM period while performing space vector modulation, we will use at least one of two, quote, null voltage configurations, which involve either all three phases being connected to high or all three phases being connected to low voltage. We will refer to these two configurations as voltage configuration 0 and voltage configuration 7. As we discussed last episode, the absolute magnitude of the voltage any phase is connected to doesn't really matter. It's the voltage differential that drives current. In both configuration 0 and configuration 7, the voltage differential across the motor is 0, and thus current is unforced, meaning it's just as free to flow as it would be if the motor leads were all soldered together. Essentially, we're achieving the same result that we had during the unforced phase of complementary switching, just with all three phases instead of just two. But when do we use configuration 0 and when do we use configuration 7? Well, the answer to this is determined by which space vector modulation pattern you choose. For instance, the quote null V0 pattern, which is generally regarded as the best choice if you're trying to minimize your switching losses, always uses configuration 0 during the whole of its unforced phase. The alternate reverse sequence, which we introduced last episode, which has less harmonic distortion, uses both, evenly splitting its unforced phase between the two. But before we can wrap this up and I can give you the PWM equations you send to your MOSFETs, there's one more thing we need to talk about: PWM alignment. A PWM signal can be configured in three different ways: leading edge or left aligned modulation, where the front edge of the period is reserved as the beginning of the high phase, and the back edge of the signal is modulated to adjust between 0 and 100% duty cycle. Trail edge or right-aligned PWM, where the end of the period is reserved as the end of the high phase, and the location of the left rising edge is varied to adjust between 0 and 100% duty cycle. And finally, pulse center or center-aligned PWM, where the center of the PWM period is reserved as the center of the high phase. Here, the locations of both the rising and falling edge are varied in unison to adjust between 0 and 100% duty cycle. In general, when discussing PWM signals broadly, unless otherwise specified, left-aligned PWM is the default assumption. With space vector modulation patterns, however, our PWM signals generally need to be center-aligned. Awesome. Now we finally have all the background information covered so that we can describe how to send the space vector modulation signals to our H-bridge. So the first thing we need to do is configure our PWM settings to be center-aligned. Next, we need to calculate the desired vector orientation and the duty cycle. The orientation will typically be decided by your rotor position, but can also be influenced by any desire to, say, field weaken. Meanwhile, your duty cycle commanded will be an output of your current controller, as we discussed last episode. Using these values, you can then calculate the time you want to spend in each of your force configurations, as well as your null vector. T1 will be equal to your PWM period in seconds times your duty cycle times the sine of 60 minus the angle alpha. This alpha value is how far your desired vector is past the vector in which you will spend T1. Mathematically, this can be easily calculated by finding the remainder of your desired vector angle divided by 60. T2 will then be equal to your PWM period, again in seconds, times your duty cycle, times the sine of alpha. And finally, T0, which is the time you'll spend in your null vector, is equal to your total period T in seconds, minus T1 and T2. Now, while these voltage configurations we've been talking about are, at least in my opinion, helpful for us when understanding what's going on, microprocessors require you to specify your PWM periods in terms of how long each phase will be written to high or ground. So, to convert from these configuration periods into the actual PWM signals you send to your H-bridge, we will use the following piecewise function. There are two things worth noting here. Firstly, if you want your vector to point strictly in the rotor's q-axis direction, you can think of these equations in terms of Hall sectors, where each set of equations corresponds to a different sector. Secondly, and very importantly, these equations are for the angle convention I have adopted. Other resources may define what angle they call 0 or which Hall sector they refer to as 0 differently than I do. This will cause their equations to be phase shifted relative to mine. My angle convention isn't more or less correct than anyone else's, but it's important that whatever convention you choose, you're consistent with it. To help better visualize what these PWM output signals will look like, I will show the PWM signals of each of our 3 phases as we shift the orientation of the rotor. Note that the upper position indicates a leg of the bridge being connected to high voltage, while a low position indicates it being connected to ground. And for the whole of this animation, we're commanding a 50% duty cycle. So, these equations may seem like a lot of math, but the good news here is that most microprocessors are pretty good at doing math very quickly. So, if you have a chip that's capable of these calculations at speed and a way of measuring motor angle with a pretty decent resolution, you're on your way. It's worth noting, and we're going to talk about this in a later episode, but if you have multiple pole pairs in your rotor, you will need a higher resolution angular measurement, since all of the angles we've been talking about are magnetic angles, not mechanical angles. But that's it. That's the basics of how to optimally control your brushless PM-DC motor. And this is kind of the culmination of this video series. That said, we're still going to have a couple more episodes coming out. You can kind of think of these as an epilogue, where we're going to look into some other practical concerns and topics and try to tie up any odds and ends that may still be confusing. Next episode, we're going to start by talking about something super practical: motor datasheets, how to read them, and what values are of the most importance to you. So, thanks for watching, and see you next time.